Bootstrap is very important concept in machine learning. In this video, mostly I explain the Bootstrap for cross-validation purpose, but we can use Bootstrap in many different applications like reinforcement learning and other machine learning approaches. So it is very important to understand what is Bootstrap and when we can use the Bootstrap method. So basically for machine learning, we collect the data. Let's say we have n number of data and each data has pairs, input and output with index of x1, y1, x2, y2, x3, y3, and so on, so up to xn, yn. This is a data set, and common assumption for this data set is each data point is IID from some data generation process. So there is some data distribution D, and each data point follow the D distribution. That's fine. And from this distribution or from this observation, we want to train some our algorithm. Machine learning is basically train some given model using the training data point. And cross-validation, we want to estimate the test error, not the training error. So we usually use some independent data set to estimate the test error of the trained model. That's it. And what is Bootstrap? Bootstrap is, suppose we have a model fit to a set of trained data, and we have the data for training the model. The basic idea is randomly drew data set with replacement. So random sampling with replacement. This is Bootstrap policy to generate new data set. Okay. So here we have n data point. From this n data point, we can generate a new data point or new data set. How to generate the new data set? Essentially, we randomly select one of data point among n existing data point. Pick one of them. Let's say this is x prime 1, y prime 1, which comes from one of data point in your training data set. Forget about the first selection and then again sample new data point x2, y2 prime from the n training data point. So essentially at each time with probability 1 over n, each data point can be choose. So with uniformly distribution, we choose one of data point to add one data point for the new data set. When you repeat this process n time, you can fill the data set, new data set with n data point. But remember, we are using random sampling with replacement. So the same data point can be sampled 2 times or 3 times or 4 times. Okay, so among n data points, there can be many duplicated data which occur several times. Okay, so in this process, with this process, we can generate new data set as we want. We can generate data set 2, data set 3, and so on, right? And this data set generated by some d-hat distribution, and the d-hat distribution is again another data generation process which organized by the empirical observation already existing n data point. So let's use a very simple model to understand more easily. So let's say we have only one single input predictor x, and for the input x we can draw some CDF value. So CDF is value from 0 to 1, which define the data generation distribution. Okay, so this is the domain of your input, and the value will be between 0 and 1. So when you know the exact CDF function, you can construct the data generation process D, and you can draw random data set infinitely many as you want. And there is no problem if you know the CDF exactly. You can generate many new data points which follow the real data distribution. So you can essentially you can accurately estimate the test error as well, because you know the new data point distribution, so you can simulate your trained model with very nice simulation environment. So for instance, if you construct infinite number of data points for your training and infinite data point for your test, and all from the given known distribution, you can very accurately train your model, and you can test the trend model with very accurate estimation. But the problem is we don't know this exact distribution, but we just have the n training data point. From the n training data point, we can estimate the CDF. Essentially, each observed data point can generate this kind of stepwise CDF value according to your observations. If n is sufficiently high, we can very accurately reconstruct the original true CDF. If n is small, then very rough idea we can have for the CDF. So there may be a huge error. Okay. Anyway, so from the n observation, we can roughly construct the CDF function, and from that we can generate a new data point that follow this constructed CDF, that is bootstrap. Using the given training data point, at each time we randomly select one of the data point and construct n data point to build a new data set. We can use newly built data set for your training, and you can do this process multiple times using different data set. Why this is good? Since we can repeat the training process many different times using very similar statistics with original data set, we can basically understand the statistics of your learned parameter. You can understand the variance of beta 0 hat, variance of beta 1 hat of your logistic regression, your linear regression, your LDA, your QDA, and so on. You can understand all the variance of your parameters. That was a very difficult task without Bootstrap. With Bootstrap, you can generate new dataset very easily. So you can implement many different independent learning process. From that, you can understand statistics of your learning process. That is very important. And Bootstrap basically indicates such things. When you reuse the same dataset several times, you can understand the statistic of your learning much better than before. And reusing the same dataset again, which the name of this process is Bootstrap. Okay? Right. And you can use the Bootstrap for your cross-validation purpose. Essentially, in the the learning process or bootstrap process, you have n data point, and every time you pick one of data uniformly random. After construct n data point, because we allow the repetition, replacement, some of them sampled several times, but some of them maybe never selected. This is called out of bag. So using the sampled, collected data, you can train your model, and then you can test your trained model using out of bag. So that is one cross-validation process using Bootstrap. And one good news for bootstrapping method, you can build dataset as many as you want. So you can repeat this process again and again and again as you want. So this very similar with the k-fold cross-validation. At each time, you randomly split your data as training and test. Random sampling with replacement, bootstrap method. You train model and then test the model. Train model and test model. And then average out the estimated test error. From that, you can understand the real test error. Of course, there is some bias and there is some error on your estimation, but in practice, this process will give you reasonably good estimation on the test error. Okay. Then what is the size of out of bag? You can compute the expectation of the size of out of bag. Essentially, the probability one element not belong to the bag, the one data set by Bootstrap is 1 minus 1 over n to the n, because 1 over n is the probability this given item is given data point is selected by uniformly random sampling. And we learn this sampling process n times. So the probability this item not belong to this data set is 1 minus 1 over n to the n. This is approximately 1 over e, right? And this is equal when n goes to infinity.